With the utility of the radian measure of an angle, we can find a useful formula for the arc length of a circle. Here's the formula. The length S of an arc intercepted by a central angle of alpha radians on a circle of radius r is given by the formula S equals alpha r. Please memorize that very important and useful formula. Let's talk about where it comes from. First of all, we are looking at calculating the length of the arc on a circle. Let's consider the ratio of the length of that arc to the entire circumference of the circle. The circumference of a circle of any radius is calculated as 2 pi r. That ratio is equivalent to the central angle subtended by the arc S, which in this case is alpha, divided by the central angle subtending the arc spanning the entire circle. That is an angle of 2 pi. Notice if we multiply both sides by 2 pi, we ultimately lose that factor. And then we can multiply both sides by r to obtain our formula S equals alpha r. So the length of the arc is directly proportional to the product of the angle in radians and the radius of the circle. Again, this is not a unit circle specifically, this is any circle. What's really important to recognize about this formula is that it only works for angles measured in radians. In the derivation of our formula, we made an assumption of alpha in radians with this factor right here. If the angle is measured in degrees, instead of having a 2 pi on the bottom, we'd have to have a 360 degrees on the bottom. If the angle is given in degrees, then we're going to have to convert it to degrees in the formula. So we're going to take the angle in degrees alpha, we're going to convert it to radians by multiplying by pi over 180 degrees times r. So we're going to have this extra conversion factor in the formula. This is one instance among many where you can see that using the radian measure of an angle certainly simplifies a formula. That'll happen quite often. Now, let's use this in a real-life application. Example 6. Peshtigo, Wisconsin is on the 45th parallel. This means that an arc from Peshtigo to the North Pole subtends a central angle of 45 degrees as shown in the figure. So if Peshtigo is on the 45th parallel, and we're talking about latitude here, then the angle that subtends the arc from the North Pole to Peshtigo then is this 45 degree angle. If the radius of the Earth is 3,950 miles, and we're going to use that measurement quite a bit in this class, then how far to the nearest mile is it from Peshtigo to the North Pole? So on the picture here, we can see that the radius goes from the center of the Earth out to Peshtigo or to the North Pole on either side. Let's simplify this picture a bit by taking it off of the globe and drawing a simple angle which subtends an arc. So our central angle is 45 degrees. We're interested in the distance from the North Pole to Peshtigo. That's going to be an arc on a circle because the Earth is round, and the radius here is 3,950 miles. So to calculate the arc length, we're going to use our formula S equals alpha r. However, alpha, the angle, is given in degrees. Let's just go ahead and convert that to radians. In radians, 45 degrees is pi over 4, and we can multiply by 3,950 miles. We are going to round this to the nearest mile, so I'm going to pop over to the calculator and evaluate pi divided by 4 times 3,950. Rounding to the nearest mile, we get 3,102, or 3,102 miles away. So once again, please be sensitive to whether your angle is given in degrees or radians. Let's try another interesting example. Maybe this one will help all of you flat earthers out there to make some concrete calculations to show that the earth is in fact round. Example 7. Over 2,200 years ago, Eratosthenes read in the Alexandria Library that at noon on June 21st, a vertical stick in Syene cast no shadow. So looking at the diagram here, we've got Syene right here. The vertical stick, when it's exactly 12 noon, does not cast a shadow because the sun is directly overhead. So at June 21st at noon, Eratosthenes set out a vertical stick in Alexandria and found an angle of 7 degrees in the position shown in the drawing. So at the right time, he sets a vertical stick in Alexandria and measures that 7-degree angle. With this assumption, Eratosthenes reasoned that since the sun is so far away, sunlight must be arriving at Earth in parallel rays. With this assumption, he concluded that the Earth is round and the central angle in the drawing must also be 7 degrees. So notice we've got a vertical here going from Syene to the center of the Earth. We've got a line in the direction of the stick in Syene, and we are assuming that the sun's rays are parallel to the rays in Syene. So if this angle is 7 degrees, notice we have 2 parallel lines cut by a transversal, and we know that alternate interior angles are equal. So both of those angles will be 7 degrees. Now, Eratosthenes then paid a man to pace off the distance between Syene and Alexandria and found it to be 800 kilometers. Assuming that the Earth is round, that's going to be an arc on a circle. So that arc is 800 kilometers. From these facts, calculate the circumference of the Earth to the nearest kilometer as Eratosthenes did, and compare his answer with the circumference calculated by using the currently accepted radius of 6,378 kilometers. So from our diagram here, we can calculate the radius of the Earth using our formula S equals alpha r. However, because alpha is given in degrees, we are going to need to convert it to radians. So we're going to take our 7 degrees and we're going to convert it to radians by multiplying by pi over 180 and then multiply by the radius r. And let's come over here and replace S with 800 degrees. Solving for r, we're going to have 180 times 800 divided by 7 pi to get the radius of the Earth. Now, be careful when you plug this into your calculator. Make sure you get that operation in the denominator in parentheses. So we'll evaluate 180 times 800 divided by, in parentheses, 7 pi. We come up with 6,548 kilometers to the nearest mile. 6548. So approximately 6548 kilometers. The actual currently accepted radius in kilometers is 6,378. So not bad for 2,200 years ago. If we then plug this into our circumference formula, 2 pi r, then Eratosthenes would have calculated the circumference of the Earth to the nearest kilometer to be 2 pi times his result of 6548 for the radius to get 41,142 kilometers. For the circumference of the Earth. Let's go ahead and calculate the actual circumference. That is 2 pi times 6,378 kilometers. 2 pi times 6,378. So the circumference is 40,074 to the nearest kilometer. Again, I'd say that's not a bad approximation from 2,200 years ago. Remember, he didn't have a TI-84 to do his calculations for him. So in this section, make sure that you know your arc length formula, S equals alpha r, and again, be sensitive to whether your angle is in degrees or radians. To use this simple formula, make sure you convert that angle to radians.